so let's take a look at the actual cooling process. We're going to change it around slightly because in this situation, any energy lost by the aluminum went into the water. The water was enclosed. There was no energy lost into the big environment. Let's change it slightly, and now we're going to put the hot piece of aluminum into a really big open space or into a big pool of water, something where the amount of water is vastly larger than the cube. In other words, one where the temperature of the water is not going to change significantly because you have so much water, the energy gets spread out over a lot more particles. Personally, I always picture it as a hot cube put in the middle of the room. The average temperature of the room is not going to change significantly because I have a small piece of hot metal sitting in the middle of it. I will start it out at 60 degrees Celsius. We'll keep it as aluminum. And 50 grams, although the 50 grams is not particularly significant here, into big open space. After 10 minutes, the temperature is now 40 degrees Celsius. And I just made those numbers up. I know it's cooling down. Put it in big open space, I do need to tell you that's at 20 degrees Celsius. Question is, after another 10 minutes, what is the temperature? It is not 20 degrees Celsius. So this gets into what's known as Newton's law of cooling. And you'll be able to see this on Friday. It's not part of the lab, but you'll have a thermal probe in the boiling water, and then you can just take the thermal probe out of the boiling water and set up the lab quest so that it will record the temperature, and you can see how the temperature changes. So if this aluminum is at 60 degrees Celsius, and I'm putting it into a big open space at 20 degrees Celsius, and again, big open space indicating that, or implying that this number is not going to change any. What is the coldest that aluminum is going to get? What is that? The minimum temperature. Yes, it will not get colder than the room. As with all thermodynamics, you should always tack on, statistically speaking. So my aluminum, the temperature of the aluminum, in degrees Celsius, we started out at 60. 20 is the bottom. It's the absolute smallest it will get. What Newton claimed is that it will get closer and closer. At some point, we can't differentiate it, but it actually curves as it gets closer and closer. This is an asymptote. And he makes the claim is that the aluminum is going to lose the same percentage of temperature in the same time increment. So let's think about that. So the first 10 minutes, what was the change in temperature of the aluminum?
20 degrees Celsius.
Technically negative, but we don't have to worry about the negative signs would all cancel out. What is the maximum amount of temperature that it can lose?
After 10 minutes?
No, I mean, it starts out at 60 and it's going into a room at 20. What's the maximum it could possibly lose?
40 degrees Celsius.
I think two of you said the same thing.
40.
Sorry. Yeah, 40.
Yeah.
So what Newton is claiming is that in 10 minutes, assuming that information is correct over there, in 10 minutes, I'm going to lose that fraction. I'm going to lose half of what I possibly can lose every 10 minutes. So second 10 minutes, the temperature is now 40 degrees Celsius for the aluminum. What is the most it can lose?
10 degrees?
You jumped ahead. Yeah, the most it can lose is 20. The actual change in temperature is, well, we've got a fraction here. That's where the 10 comes in. So after another 10 minutes, this is now 30 degrees Celsius. We can keep going. The next third 10 minutes, well, I know it's going to lose half of what it can lose. So what's the most it could lose? We're now at 30 degrees.
15. You said half?
It's not half of that number. It's half of what it possibly could lose.
Okay.
It's now 30 degrees Celsius in a room that's 20 degrees Celsius.
10.
So it could lose 10 degrees Celsius. Again, that's the maximum they could possibly lose. And so now the change temperature is 5, not meters per second, 5 degrees Celsius. So it's going to lose 5 there, so now it's going to be at 25. And it's going to lose half every single time, given my initial setup. So after another 10 minutes, it'll be 22.5, and then 21.75. It just keeps getting closer and closer. In this nice ideal situation, it never actually gets there. But at some point, it becomes indistinguishable. So if I had some sense of plotting properly here, let's see how well this will actually show up. So these will be 10-minute increments. So time in minutes. So 10, 20. So at time 0, it's at 60 degrees Celsius. At 10 minutes, it's at 40 degrees Celsius. At 20 minutes, it's at 30. 30 minutes, it's at 25. 40 minutes, it's 22 and a half. And logarithms are involved if you actually went into the calculus of it. Or exponentials, depends on how you want to look at it. One of the problems in the textbook that Hewitt gives, unfortunately, he picks numbers. It's one of the assigned problems, but he picks numbers where if you don't know what you're doing, you can come up with the same numbers several different ways. And it's sort of misleading. That's why I like to use numbers where there's not a lot of duplicates there. It's unfortunate that that happened right there. So let me come up with, let's do it again, come up with numbers that are not going to work out nicely, or that won't duplicate, I should say it that way. Keep that at 20. Oh, nope, sorry. At 60. At 50. So I want you to predict what is the temperature after that second 10-minute interval. I'd like you to sort of work on it on your own, at least set up. If you don't have a calculator, just set it up. If you do have a calculator, just come up with an answer. The people are really close here, so let's take a look at it as a group. So the actual loss the first time was 10 over a possible 40. So that fraction should work for the rest, for every 10-minute period here. And so then, the most you could possibly lose for the next 10 minutes is 30, because you're now at 50, the difference between these. And so delta T is 7.5 degrees Celsius. And so you're losing, so 42.5.
And then do we just subtract 7.5 from that number?
The 50, yes.
No, like for the next time, the 42.5.
Oh, for the next one, you still have our fract. Every 10-minute period, given the way I set up the problem, you're going to lose a quarter of whatever temperature you could lose. So that would be equal to the next 10 minutes. The most you could possibly lose is 22 and a half. And so delta T is
5.625.
5.61. And so minus 5.6, 36.85 for the next round, after the next 10-minute period.
Why did you put 22.5 on there? You just dropped it to 30.
So, because we're at 42 and a half at this point, and the most, again, we're working on the assumption the temperature of the room is not changing.
Okay.
So the most it could lose is 22.5.